Hello everyone. So this is a question from NEET 2026. Compound P C8H8O gives a red-orange precipitate with 2,4-DNP reagent and it does not reduce Fehling's reagent. Okay. On drastic condition with chromic acid, important, P gives an aromatic product Q that produces effervescence on treating with aqueous NaHCO3, sodium hydrogen carbonate. So P and Q respectively are. Okay. So the chapters involved is aldehydes, ketones, and carboxylic acids. Okay, and these are the options. So to start with, only aldehydes and ketones react with 2,4-dinitrophenylhydrazine, which is also known as DNP. And DNP is also known as Brady's reagent. Okay. So only aldehydes and ketones react with 2,4-dinitrophenylhydrazine, which is our DNP, and it is also known as Brady's reagent. Okay, and aldehydes and ketones will react with DNP to give us yellow, orange, or red precipitate, to give yellow, orange, or red precipitate of 2,4-dinitrophenylhydrazones. 2,4-dinitrophenylhydrazone, which are also known as DNP derivatives. Okay, so this is an important fact to know, that only aldehydes and ketones, they will react with DNP to give yellow, orange, red precipitate of 2,4-dinitrophenylhydrozones, which are known as DNP derivatives. And this reaction, that is the reaction between aldehydes and ketones with DNP, is an example of nucleophilic addition reaction followed by elimination of water. Okay, so we'll see some examples. For example, let's take the case of an aldehyde, CH3 C double bond O H. So this guy is obviously ethanol, so it will react with DNP, which is 2,4-dinitrophenylhydrazine. The structure is, we'll have a benzene ring, NO2 on 2,4 positions, and we'll have NH and NH2. So this is our DNP. Okay, and whenever they react, it happens in acidic conditions. So to get the product, what we do is we write down the partial charges. So here the partial charge is positive because carbonyl carbonyl oxygen will take away these electrons, so therefore partial negative. And I can separate this hydrogen from NH2 to show that this hydrogen is positive charge and this nitrogen is lone pair, so it will have a negative charge. So what will happen? Look at the arrows. This hydrogen is given to this O. This lone pair is making a bond with this C. So we will ultimately get CH3C. So we'll show this by arrow. So we'll get CH3COH. One H bond is there. And the new bond between C and N, which will have one H connected to NH, which is connected to benzene ring, NO2 and NO2. Okay, and also it will ultimately result in loss of a water molecule, OH from here and H from there. So the final product is going to be CH3 CH double bond N NH benzene ring NO2 and NO2. So these are known as DNP derivatives. Okay, and obviously a molecule of water. Okay, similarly, so this was an example of aldehyde. Similarly, ketones also react with DNP. Okay, so for example, CH3 C double bond O CH3. So this guy will also react with 2,4-dinitrophenyl hydrazine, which is NH2 NH benzene ring NO2 NO2 in the presence of acidic conditions, and the product that we'll be getting will be CH3 CH3 double bond N NH benzene ring NO2 and NO2 plus H2. Okay, so in a nutshell, from this particular point, it is proved that P is either an aldehyde or a ketone of the formula C8H8O. The next useful information that they have given us is that P does not reduce Fehling's reagent. Very important. Now, when aliphatic aldehydes, these are those aldehydes which don't contain any aromatic ring. So when these guys are heated with Fehling solution, okay, so when we react it with Fehling's solution, this Fehling solution is reduced to give us a red precipitate of cuprous oxide. Okay, so this is reduced to give us a red precipitate of Cu2O, that is cuprous oxide. Okay, aromatic aldehydes don't reduce Fehling solution, very important. Don't reduce Fehling's solution. And obviously ketones, whether they are aliphatic or aromatic, don't reduce Fehling solution. Okay, and this is because Fehling solution is a weak oxidizing agent, so it does not work with ketones. Okay, so from this information you can see aliphatic aldehydes, it reduces Fehling solution to cuprous oxide. Aromatic aldehydes don't reduce Fehling solution to cuprous oxide. Ketones also don't reduce Fehling solution to cuprous oxide. So therefore P is either an aromatic aldehyde or a ketone. Okay, so it is either a aromatic aldehyde or it is a ketone. Okay, cool. Then the next information that is given to us is that P on drastic oxidation, that word is very important. Drastic oxidation with chromic acid. Okay, chromic acid has the formula H2CrO4 and its structure is Cr double bond O double bond O OH single bond OH. So this is the structure of chromic acid and it is a powerful or a very strong oxidizing agent. Okay, and it is made by mixing K2Cr2O7, that is potassium dichromate, with concentrated sulfuric acid, that is H2SO4. Okay, so this guy is made by mixing K2Cr2O7 plus H2SO4. Okay, so from this observation, P is a ketone. We are sure about it that P is a ketone. Okay, so I'll explain how. Because to oxidize P, first of all, there is drastic oxidation. Okay, and also we are using we are doing the oxidation with a strong oxidizing agent. Okay, only in the case of ketones we have to use a strong oxidizing agent to oxidize them, because we have to break C bonds in the case of ketones. Okay, for example, ketones are C double bond O connected to carbon, connected to carbon. So to oxidize them we have to break either this bond or this bond, which is a CC bond. You can see. Okay, hence severe or drastic conditions are required and also strong oxidizing agents are required. Okay, but to oxidize an aldehyde, let's take an example of a aldehyde, C double bond O connected to C and H. Okay, a weak oxidizing agent is enough, because the hydrogen atom on the carbonyl group, that is this guy, can be converted to OH group by breaking this bond. So there is no need to break any CC bond in the case of aldehydes. So therefore, normal conditions and even a weak oxidizing agent is enough to oxidize aldehydes. In this question, we are using drastic conditions and also a very strong oxidizing agent. So therefore, P is a ketone. Cool. Now, P upon oxidation gives an aromatic product Q. Very important. Whenever you oxidize P, we are getting Q, which is aromatic. So therefore, P also has to be aromatic. Okay. So therefore, P is a aromatic ketone. Okay. And its formula is C8H8O. So the aromatic ketone with the formula C8H8O is this guy. Benzene ring, C double bond O, CH3. So this is P and it is known as acetophenone. Okay, cool. Then obviously we are oxidizing it with chromic acid. So obviously whenever we oxidize ketones, the rupture or the breakdown of CC bond occurs. So either this bond is going to break or this bond can also break. Okay, the CC bonds are going to break, and whenever we oxidize ketones, CC bond breaks to give a mixture of carboxylic acids. So whenever we oxidize ketones, we get carboxylic acids, and those carboxylic acid will have less number of carbon atoms than the original ketone. Okay, you will see the reason. So here the number of carbons are 1 2 3 4 5 6 7 8. Okay, so there are total 8 carbon atoms. We'll see the product. Okay, so let us write down our ketone, which is C double bond O, CH3 and benzene ring. Okay, so let's say if this bond breaks, so we have H2CrO4, and let's say A breaks through this path, and let's say we are reacting it with H2CrO4 chromic acid, and let's say B breaks through this path. Okay, so when A breaks, you can see this is A path. So this part will give me one carboxylic acid, and this part will give me another carboxylic acid. Okay, so carboxylic acid corresponding to 7 carbon atom is benzoic acid. Okay, so if we follow path A, our product, one of the product is going to be C double bond O, OH. So this is known as benzoic acid, and the other product is going to be from this part of the ketone, so having one carbon atom. So therefore we will get HCOOH. Okay, so this is our Q benzoic acid. Okay, then what about this path B? Okay, this won't happen, this bond won't break, because if you remember, there is resonance here, so this double bond can come here, and because of resonance there is a double bond character on this bond, and to break this bond it is going to be very, very difficult. Okay, so therefore this does not happen at all due to double bond character due to resonance. Okay, so therefore now you can see we started with a ketone having 8 carbon atoms, and we are getting the product carboxylic acid. So this guy has 7 carbon atom and this guy has 1 carbon atom. So that's why this statement that CC bond breaks to give a mixture of carboxylic acid, and they will have less number of carbon atoms than the original ketone. Okay, and hence our aromatic product Q is benzoic acid, and obviously benzoic acid will react with NaHCO3. It's an acid, this is a base, so they will react with each other. Okay, and we will get salt, C double bond O, O, Na, plus H2O and plus CO2. So CO2 is a gas, and because of this we get effervescence whenever we treat Q with NaHCO3. Effervescence are basically bubbles coming out. Okay, so therefore our P is acetophenone. This is P, and our Q is benzoic acid. Okay, so therefore option D is the correct answer. In option D we have P as acetophenone and Q as benzoic acid. Okay, so therefore D is the correct answer. Thank you.